want to improve your compression. The details are not that important, actually. It's important what kind of data your algorithm can pack and what kind of structure you can exploit and what works well and what doesn't. And transforms are the key to that. This is what makes a huge difference. This is what makes the difference between an intro that is 64 kilobytes and an intro that is 80 kilobytes. You don't have to overdo it. Simple transforms are usually best. And it's very easy to do usually. Reordering in this LZ and context-based schemes is very powerful and again usually simple to do. And the key to that is grouping data by structure and optionally doing some very simple scheme like delta coding afterwards. And for all you do, you really have to measure if it gives you a gain or if it's just a waste of code size. You want to be sure that everything you do is actually worth it. And finally, these examples of some of the things I did. I didn't want to overload this talk with too much information. I hope that the ideas came through and the general design strategy, the kind of stuff that you have to try to understand the type of data you're doing and try to make the packer understand the type of data you're trying to compress, because that's what actually gives you compression gains. Still, it's heavily dependent on the type of data, how much you can gain. Your mileage may vary on that. Okay, so final questions and answer section. Any questions? Come on. I don't believe you. Yeah.
But explicit and implicit dictionaries, the compressors, you said there's advantages to code the references so that they are as short as possible for those for those entries which come often, and it's possible with schemes with explicit dictionary. But with implicit dictionary, am I understanding this correct? That arithmetic coding or similar systems that are afterwards do mostly the same, with an added benefit that it also works for the data.
No, the actual benefit in doing implicit versus explicit coding and that kind of framework is that in explicit coding, you just get a sequence of coded strings. You fill up your dictionary initially with single characters and add longer strings as you go. So you always have codes in this dictionary and you never leave it. The advantage of implicit coding is that for every character, you can actually decide whether it's worthwhile to code a match reference or just use the arithmetic or Huffman code or whatever you're doing. That's what gives you the difference, and that's what makes it easier to integrate. Because when you have Huffman coding, say, on the explicit dictionary, you have to code all the dictionary entries. And this can be a large number, and it can be hard to get statistics and that kind of stuff. The advantage of implicit coding is that you can really keep the dictionary scheme and whatever else you're doing separate. That's what gives you the advantage in coding, because you can just decide on a case-by-case basis what is the better idea to code something. Okay? Any other questions? Yeah?
Did you also investigate Burrows-Wheeler transformation or something like that? Or do you know of any packer that uses it?
Yeah.
Execution packer, of course.
Yeah. BZIP uses it, and the problem is, in an intro context, it's not really useful. A Burrows-Wheeler transform is a very interesting algorithm, a very interesting transform algorithm actually, another actual coding algorithm. But the problem is that it really just works well for large amounts of data. Say you need a few hundred kilobytes at least. I've done a lot of experiments with that kind of algorithm, but I've never managed to get interesting compression rates, like a lot better than LZ schemes, in an intro context. So just not used it so far. I've done some experiments, but it's usually not worth it for intros. Yeah?
Have you ever thought of writing your own kind of virtual machine with your own opcode?
We've thought about that. We actually started writing a forth-based intro system with some kind of forth, if you don't know, it's a stack-based language. But the problem is that writing intros in this kind of language is really a pain in the ass. And you don't want to do this. So we tried this for a few months, but it really wasn't worth it. It wasn't worth the work. It wasn't worth the gray hairs. So we just skipped it and said, okay, we still use C++ and try to make C++ compiled code compress as good as we can. But I know some people who've tried successfully to use it for case. So it can actually work, but it's really, really, yeah, it's basically annoying to code that way, at least for larger projects. Okay. No questions anymore? Yeah?
Just one quick question about interrupt-free stuff.
Yeah.
You said like 3 slides before.
Yeah.
That's just something that you use to find the begins of functions. That
Yeah.
Okay, so it's just something.
This is
you
just.
don't use it. It's not really anything used for compression. It's just.
It's just something. That's an interesting property.
Structure.
Yeah, that's an interesting property of Visual C++ compiled code that I can easily use to deduce beginnings of functions, because you usually don't have breakpoint opcode, so that the whole code I can just treat as if it was a beginning function marker. So it was kind of neat, but it's not necessary now. Yeah.
Why didn't you use the map files coming from the compiler?
I use them too. But the problem is, the interesting thing about this code stream thing, you need to undo all the transform stuff in the depacker. Everything that's in the instruction stream, like in 3 opcodes, I get anyway. I don't need to code them explicitly. When I do a map file, I need to store that map file information separately, so it gets bigger. Okay? Yeah. And yeah, Ronnie was just winking to me I should stop. If you have any further questions, we can just do it here, but another seminar has to start soon, so that's the end. Thank you for visiting.